This is Josh White with JW Math Tutoring. In today's video, I'm going to go through some advanced quadratic function techniques that you can use in Desmos to help solve some of the hardest digital SAT math problems. So let's go ahead and take a look.
But life is a dream that calculus could never predict.
This is part 13 of my ultimate Desmos guide to digital SAT math. And in this video, I'm going to go through and summarize some of the common advanced quadratic function problems that you can solve. All right, so some of them are going to be separate, like the first type and the last type. But there's two in the middle that are kind of related, and even though I have them split them up into two different topics, they're really one and the same, and the same methods apply to both of them. Okay, so the first type we're going to look at is finding the values of a constant in a quadratic solution or equation. And actually, before I begin that, just do have a couple other things to mention. First, if you like this video, of course, please do give it a thumbs up, subscribe to my channel, and sign up for notifications. Second, under each topic, it shows which part of the guide this was already covered in detail. Most of this will be review, so I'm not going to go through it as in-depth as I did in previous videos. So just keep that in mind. If you want to see more detailed examples, like it described in greater detail, go check out the specific part of the Desmos guide that you see underneath the topic. Also, of course, there'll be a PDF file for this linked in the description and also in the pinned comment of the video. And there are some example problems I'm going to go through, but again, I'm going to go through them fairly quickly just because I do have other examples, like I said, in the various parts of the guide. All right, so first type, it's finding the value of a constant in a quadratic solution or equation. Basically where you have to be given an equation, you have to be given a possible solution. And one of them has a constant in it. Now, there is another example, which is where you have two constants. That actually is new, so that I will go over in more detail. But the first type is where you just have one constant. And there technically are two methods to do this. They're listed in my full guide in the PDF file. I go over both of them in the example video, part 9, but I'm just going to focus on the one that I prefer here, which is to take the equation that you're given, make sure that everything is equal to 0, type that equation as a function, f of x, and then you're going to take the solution that you're given and type f of whatever the solution is and use regression tilde 0. All right, so just to go now and look at an example problem for this type. This is number 1 here, this first problem. So you have an equation, and they tell you one possible solution is, this, -1 minus root c over 4. What's the value of c? Okay, so note, one thing you do have to do is you do have to get the 21 over to the other side so it's equal to 0. And then you can set this equal to f of x. All right? You don't have to distribute the x. You can just leave it as it is. Okay? So that's what we enter in as f of x. And then the second line, we just do f of. And now I type the solution that I'm given. And then we use regression, and we tell Desmos that this solution will give us a 0 as an output. And there we have our answer. The value of c is 29. Okay? And that's it. That's all you have to type into Desmos. There is no more work that is required. All right, so now let's go back to the sheet and let's talk about, this is the one thing in this video that is brand new that I have not covered previously anywhere. This is a method that you must use when you have two constants. So for example, this is the same type of problem, except that now maybe in the solution they give you two constants, and we'll go back and look at the same problem and work through it. Basically, if you have that type of problem, what you technically have to do is you have to take the given solution and then you have to find its conjugate, and you have to basically solve both of them in a system of equations using regression. Okay? So you can see an example of how it looks on the screen here. So now let's go back to the problem, and I'll show you exactly what I mean. So in number 2 here, okay, let's say you were given the exact same problem, except it said one possible solution is, and now instead of -1 here, it just had b. Okay, so it's b minus root c over 4. All right, here's the problem if you tried to do the same approach that I just did on the previous problem, number 1. In other words, if I do everything the same, but I just change this to a b, okay, the problem is this basically returns any value of b and c that works, and notice it doesn't give us integer values. You know, we're specifically looking for integer values for b and c based on the given problem we have. So the workaround to this, or the way that you have to, at least the only way that I figured out to get around this, is we're going to enter, okay, so we have this given solution. That's the b minus root c over 4, right? Now we need to do the same thing, and let me just expand this so we can see the whole thing as I type it out. We need to do the same thing with the conjugate solution, which is going to be b plus square root c all over 4. Okay? Close this. So those are my two values, and then I can get rid of this. Now they are each going to be equal to 0. Close this. Get rid of that. Let's see what's going on here. Something's, oh, there was an extra space that was messing up the brackets. That's why it wasn't, that's why it wasn't populating correctly. Okay, now that that's fixed, there we go. So you have to type it in. You must enter it in like this, where you have like solution 1, which says the one you're given, comma, solution 2, which is the conjugate. That is typically not given. So you have to know, well, I just take solution 1 and I change the sign, you know, in front of the square root for a quadratic to get its conjugate. And then you set those, you know, using the tilde with regression, both equal to 0. And notice here now, it gives me the value of b and it gives me the value of c. I mean, this question, technically I set it up so it's only asking for c, but this is still how you have to solve it, even if you only want to know the value of c. Okay? And then maybe it would ask for b plus c or b times c or whatever, you know, combination of them, but this is the method you have to do when the solution has two constants in it. And one last thing, just to show you as well, this is not an example problem on here, but let's go back to the original problem that I had. So let me just get rid of this real quick. Actually, I could probably use the back button a bunch of times, but get rid of that. I got to get rid of this. Okay. So here, this was the original problem we had, right? And just to review, the constant could be in the equation as well. So for example, let's say this was 29. Okay, so this was given as -1 minus root 29 over 4. All right, and the constant was c. Okay, and you can see now if I just interchange those, now it can find the value of a constant in the equation itself. C is 21, right? Which matches right here, that c is 21. Okay, so that's just, you know, the constant can be in the equation or the solution is just what I wanted to demonstrate there. All right, now let's talk about the two topics that are basically related, and they have two different methods, but I prefer one method to the other. So these are listed as two separate things in the guide because one I had added initially in part 10, and then the other I actually added later when I found out about the second method, the derivative method, so that's technically in part 11. The whole basic idea is you have a quadratic expression, or basically an equation, and you want to find either the specific value, or sometimes it's the maximum or minimum value for a constant in the quadratic equation or expression to have either no real solutions, or exactly one real solution, or two real solutions. Okay? Both methods apply regardless of what problem type it is. The first method is what I call the vertex method. This one you're going to basically type the original quadratic expression. You're going to do regression. You're going to regress it to its vertex form, except the k value, the y-coordinate of the vertex, is going to be 0. And then when you do that, it will return the value of the constant. And of course, you have to add a list in order to make this work. For x1, it'll return the value of the constant that you're looking for. Okay. The second method, or I call it the derivative method, basically you're going to take the function, you're going to take the quadratic expression or equation, you're going to type it in as a function. Then you're going to add a second function, of just say g of x equal to 0, and then you're going to type what you see listed there on the screen. Note there is an apostrophe after the second f and after the second g. It stands for prime. It really means derivative in math terms. And notice you have to also use x1 in the regression statements. Again, for more detailed explanation of these methods and how you enter them in and everything, see more example problems, check out part 10, part 11 of the Ultimate Desmos Guide, where I'll go over more problems. All right, this is just meant to be more of a summary, short video. Okay, so let's look at the example problems now. Number 3. Okay, in this equation, blah, 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 b is an integer constant. The equation has no real solutions. What's the smallest possible value of b? All right, so I'm going to do the vertex method first. So everything is already equal to 0, so I don't need to rearrange anything. Also, since I'm doing regression, I need to use x1. So I'm going to take the quadratic equation, and I'm going to regress it to its vertex form. But again, the k here is going to be 0. Now I need to add the list for x1. And for these quadratics, I like to use a negative, 0, and the positive of that value. And then, you can just add in some other numbers as well. All right. So what's happening here is it gives us a value for b. Okay? This value for b, this is the exact value such that there would be one real solution. That's essentially what's happening with this vertex form regression. Okay? So now, really, if we want to see if it has no real solutions, like technically what you would want to do is you want to check on either side. So the easiest way to do that is just, and this is where vertex form is actually not the preferred method. So I would actually graph out you have to type it again to graph out the quadratic function. Okay, and so see here, it's pulling the b value from the regression, and it's right on the x-axis, meaning there's exactly one real solution. So let's see now, okay, if I set b equal to negative 51. Okay, notice now there are two real solutions. That is not what we want, okay? So now let's go the other direction. Okay, so now b is negative 50. Now notice we have no real solutions. There are no x-intercepts. So that tells me that this is the correct answer. Basically, the smallest that you can make b here is going to be negative 50. Now, let's take a look and see how we could solve this exact same problem but using the derivative method. So, what we're going to do first is, okay, type in the function, but we get rid of the x1s here. We just want x. And I'm going to use function notation. Okay, and then my second function is just going to be g of x equals 0. That is always how you do it for these specific types of problems. Then it's f of x1, comma, f prime of x1. Close the bracket. Tilde for regression. G of x1, comma, g prime of x1. Close the bracket. All right, notice it gave me the exact same b value. All right, so that's good. That means that it's working just like the vertex method did. And now here the key is you don't have to retype the function like we did in the vertex form, so it saves a little bit of work. So now you could check b equals negative 51. Nope. Has two real solutions. Okay, let's try going on the other side of it. B equals negative 50. Okay, so this is going to be the smallest possible value of b. All right, one other thing just to keep in mind is that usually when you're solving for the a constant, like say for the b term, regardless of what the actual letter is, but for the b term, the x term in quadratic, there's typically, depending on what the problem is asking for, there can be a range. So this one, for example, okay, notice it actually, so it gives me b equals negative 50.59 thing. However, if I put this in, notice what happens if I put a constraint that says b is greater than 0. So it actually then returns the same number except that it's positive. It's positive 50.59644. And all that does to the graph, notice, is it like shifts it over to the other side, right? But it's still on the x-axis. So, and this is in the notes in the guide, but I just want to also mention it briefly here. When you're looking for largest or smallest possible value of b, there is technically a range. In other words, what's going to happen with this problem is when b is from negative 50 to positive 50, the equation will have no real solutions. And then when it's less than negative 50, or, well, technically less than negative 50.59644, and greater than 50.59644, like when it's on, on the outside, so to speak, then it's going to have two real solutions. So depending on what it's what it's asking for, whether smallest possible value, largest possible value, you might have to do further inspection in the problem. So like for example here, it gives you the default value of negative 50, right? But let's say this one asks for the largest possible value of b. Well, then what I would notice, like I would check negative 51 versus negative 50. Then what you'd have to notice is that I actually want to check the positive end because the b's, again, there's always a range typically. So now, and that would tell you that like negative 50 is the floor in this example, and positive 50 is the ceiling in terms of integer values for there to be no real solutions. Okay, so just something to be aware of that makes this problem a little bit more complicated than some of the others. Now let's take a look at example number 4. Here's a very similar problem, except now the constant that we're finding is the number term in the quadratic equation, not the coefficient for one of the x terms. Basically, it's the c value instead of like the b value in the previous one. And we're also told that the equation has two real solutions. What's the largest possible value of c? Okay, so the first method would basically require us to type in the original given expression, and then we're going to regress that to its vertex form, except of course we're leaving the k value equal to 0. And then we can go ahead and type in our list. Okay, so we get an answer here of c for 56.25. So that is the value, that's the exact value, which will give us one real solution. So the question is, for two real solutions, do we want it to be lower than that at 56 or higher than that at 57? I mean, it's probably not going to be higher because then you could go 57, 58, 59, you know what I mean, and there's no ceiling. So it's probably going to be 56, but let's just graph it out to confirm. All right, so we can see right here with the c value, right, it's right on the x-axis. It's exactly one solution. So now let's lower it to 56. Okay, and we can see it goes below. We have two real solutions here. And if we went the other direction at 57, okay, there's no real solution. So as you increase it above 56.25, no real solutions. As you decrease it below 56.25, two real solutions. So the largest possible value of c will be 56. And the other thing to keep in mind is that these problems are not the same as the last one. Basically, and what I mean by that is, in the last one, typically for the b value, there is a range that the number will fall between. Whereas for the c value, it's just, it's just the floor, the ceiling, and that's it. Okay, there's not going to be a range. So the answer to this is just 56. We don't have to do any further inspection. So this problem with this method, you can see it's really not that much work because you don't have to do any rearranging of the terms or anything. But let's take a look now on how this problem would be solved using the derivative method. So first, we would just type in the original function. Then we're going to add our g of x equals 0 function. Then we can type the regression statement. All right, and then we get the same value. Notice here we already have the graph, so we don't have to spend the time typing out the original function to graph it. And again, now you could just, I mean, if you wanted to, you could just take c equals, 57 and see what happens with the graph. Or you could take c equals 56, okay? And obviously here we have two real solutions, so this is going to be the largest possible value, as compared to 57, on the other hand, would be the smallest possible value for no real solutions. All right, so now let's go back to the sheet and let's talk about the last type of problem. So this one is a little bit different. This is basically finding the value of a constant for a quadratic and linear function to intersect only once. So we still have the same two methods that I just used, in the two previous problems. So I'm not going to bother going through all of them again. I will just mention that for this type of problem, using the vertex method can require a lot more work because you now have two functions instead of one, two equations. They both have to be, first of all, they both have to be y equals. Then you have to set them equal to each other. Then you have to move everything over to one side to get it equal to 0. So you have to do all that work, yourself. Then you can do the regression to the vertex form and figure out, where the intersection, the constant value to get the intersection, having one intersection point. All right. Whereas for method 2, the derivative method, the only work you would have to do is you would have to get the equations equal to 0. Okay? So you have to get them in like f of x or g of x form, but that's it. You don't have to do any work after that. All right, so now let's go back to our last example problem here, number 5. All right, so notice I'm going to do the vertex method first. Here's all the work that you have to do ahead of time. And if you can do this in your head, that's fine, but most people probably would need to write it out. So step 1, the first equation is going to be x squared plus 8x plus 20 minus c. And then step 1, equation 2, 2x minus 5 plus c. Okay, now we have to go ahead and set them equal to each other. So just to save some time writing, what I'm going to do is I'm just going to write the equals up here. Now get rid of this. And now what you have to do is I have to move everything over to one side to make it equal 0. So that's going to be x squared. Now you don't have to combine the like terms when you type into Desmos. I'm just going to do it now. So it's 8x minus 2x is plus 6x. And then it's 20 plus 5 is 25. And then negative c minus 2c. But again, if you were just doing this in your head and you wanted to just list out all the terms without combining them, that will work in Desmos. So now you can type this whole thing into Desmos. And we're going to do regression to, again, vertex form, with the k value being 0. And now I will add my element list. Okay, so it gives me the value of c. So the correct answer to this question is positive 8. It also gives you the x-coordinate of the intersection point, which is going to be negative 3. Basically, it's h from the vertex formula here. So this h equals negative 3. That is the x-coordinate where these two graphs will intersect at one point. And just to show you that, now again, the other downside to the vertex using this method is that if you want to see the actual intersection, you have to spend time typing out the two functions. Okay, so now we can see the intersection right here, and we can see, yep, there it is. It's at -3, -3. So the -3 x coordinate of the intersection point is the same as the h value right here. Okay, so if the problem asked for that instead, you could also get that from the regression statement as well. All right, so that's the vertex approach. Now let's go ahead and do the derivative approach. So for this, all you have to do is technically do the -c and +c here, and then you can just type in the two functions. And it's going to, the other thing, like I said, where this is helpful is it's going to graph both functions right away. So we can actually see the intersection point visually. Okay, f prime of x. Oh, I got to remember this needs to be x1 in a regression statement. Then the tilde, g of x1, comma g prime of x1. Okay, so now let's see what we have going on here. Okay, c is equal to 8. That is the same answer we got using the vertex method. X1, this is the x value of the intersection point, x1, and that's just -3. That checks. The only, I guess, disadvantage to this is that, oh no, the point is clickable there. I was going to say the point isn't clickable, but it looks like it is. It does show up as clickable for this example. So, yep, there we have, -3, -3. All right, so those are some example problems for these advanced quadratics. Just want to mention for the last thing, by the way, the example problems are on the second page, just of the sheet here. Just want to mention to briefly summarize the pros and cons of the different methods. So, one advantage of the vertex method is that the regression statement might be easier to memorize or less complicated than the derivative method. All you're really memorizing, is like doing regression to a parentheses x minus h squared, and that's it. You don't have to memorize like the f and the f prime and g prime and so on. But the cons or the downsides to it are it doesn't show the graph or the intersection of the functions automatically. You have to type the function or functions in order to see that, regardless of what type of problem you're looking at. And it can require more work to rearrange either one or both of the equations to get everything equal to 0, and or, for the last type of problem, to then set them equal to each other and then get the new equation equal to 0. So there can be a significant amount of work that you have to do either by hand or before you go to Desmos to solve the problem. That's the main downside of the vertex method. For the derivative method, the main advantages are obviously you only need to get the equations into the form of y equals. You don't need to do any work after that. You don't need to set them equal to each other. You don't need to then get a new equation set equal, so it saves time in that respect. Also, it will automatically show the graph of the situation and like in the intersection point, regardless of what type of problem we're looking at. So that's another advantage, and that saves time. However, the main, I guess, downside is it could be more confusing than the vertex method in terms of the regression statement is a little bit more complicated, and remembering to put in the primes, for the f prime and the g prime as the second entries in the system of equations on each side, and basically having to memorize, that whole long regression statement. Memorizing that is definitely more difficult than just memorizing a parentheses x minus h squared. However, if you do a lot of practice problems and you're, preparing for digital SAT math section, you will see that you can actually use this derivative method, a fair amount, and once you use it, a couple times, it'll start to become much easier to memorize, and you'll become more familiar with it. All right, so I hope you enjoyed this video. If you did, please do give it a thumbs up, subscribe to my channel, and sign up for notifications. Also, if you haven't done so, check out the full Ultimate Desmos Guide to Digital SAT Math. The other, basically 12 parts that are already out there, including more in-depth explanations for some of the techniques that were covered in this video. And lastly, if you are looking to improve your SAT math score, definitely check out my official exam problem set worksheets and videos, which are basically published each month after there is an official exam. Anywhere from 30 to 40 questions that have been self-reported to have been on an exam for that specific month from both the US version and the international version. Free PDF worksheets that you can download and practice on, and then the full explanations available for free on YouTube.